To take this thermohaline circulation a little bit further, we haven't said anything specifically about the density and dependence on temperature and salinity, other than saying there is a non-linear dependence. So we will see how that works. So here is another figure showing the deep water formation sites here in the Labrador Sea and the so-called Gin Seas, Greenland, Iceland, Norwegian seas. The main thing to remember here is that the Gulf Stream brings up very warm waters and creates a lot of evaporation and high salinity, creating deep waters that sink and flow along the western boundary again, and there is this deep gyres as well. As you can see, there is recirculation happening, cross equatorial flow to the south and mixing with the deep water formation in the Weddell Sea, Ross Sea and so on in the Southern Ocean, circulating around, inundating the Indian and Pacific Oceans, converting and coming back. How do we know that the waters that sink to the bottom are getting converted back to the surface water and coming back? Because deep heavy water is heavier than the surface water. It's a very stable situation with light water on top and heavy water at the bottom. So why should the heavy water then become surface water again? Well, it's very simple. Think of this like a bathtub. If we go here and see that water is sinking, that means it is heavier than the water below. And if it is going all the way to the bottom, that means it's heavier than all the water in the middle. If the water in the middle was not getting converted back to the surface water over time, then eventually this water couldn't sink anymore because it wouldn't be heavier than the water below. The heavier water would keep on filling up and eventually it would stop sinking of water. So as long as we can go and see that deep waters are forming and going to the bottom at these few places, we know that the surface water, the deep water, is slowly getting converted to lighter water, and that's why deep water can still keep forming and sinking from the surface. The other amazing thing is that the ocean covers so much of the earth, and it's deep from, let's say, 1 kilometer to several kilometers. All that water, especially the deep water, is only being formed at these few sites. So that water is being generated at these few sites and it's getting filled, and that conversion of that water back to the surface, as we said, it's a very stable situation, so some energy must be driving the conversion of that heavy water back to light water. This happens by constant upward mixing and conversion of heavy density into lighter densities, and in fact it's somewhat of a mystery as to where this energy comes from, and the best estimate we have is that the tides that are sloshing the ocean around are able to generate it because they are not just moving the water this way and back this way without any change. It turns out that those tides are hitting the mountains in the ocean, like the mid-ocean ridges in the Atlantic, Indian and Pacific Oceans, where they are generating waves which break, and that energy of the waves is converted into mixing of the waters. So heavier waters are mixed with lighter waters with even lighter waters. So slowly over hundreds and thousands of years, that water gets converted back to surface water, comes back out, and then goes back to the formation sites. So you can see the sinking here in terms of depth and salinity. So this is the Atlantic section. Salinity in grams salt per kilogram of seawater section through the Atlantic at 18 west as a function of latitude and depth. So this is where we said deep water is forming. So you can see the high salinity penetrating deeper here, extending across the equator into the southern hemisphere, whereas the lighter salinity water is extending northward. Of course, in the subtropical gyres, which are evaporative high pressure downwelling Hadley cell regions, you have locally very high salinity, but even there are contrasts of salinity in the subtropical gyres of the Atlantic versus the Pacific Ocean. So this clearly shows you how the thermohaline circulation is working, and this is another way to look at it. So we have deep water formation there, sinking coming across the equator into the Southern Ocean, inundating the Indian Ocean and the Pacific Oceans, converting into surface waters and coming back out. So the Pacific water is coming through the Indonesian seas, mixing with the Indian water and mixing with the water that's circulating in the Southern Ocean and going back to the North Atlantic deepwater formation site. Okay, so how to think about the density of water? Here we are looking at salinity in parts per thousand. So salinity is typically in non-dimensional parts per thousand dimension. So non-dimensional dimension. Here is temperature. So you can see these constant density lines for a combination of temperature and salinity. Okay, so you can see that classical oceanographers, hydrographers, they look at the temperature and salinity and the density, and they can identify the water masses. So Antarctic intermediate water is on this density line here at this salinity and this temperature. The North Atlantic central surface water, which is coming out of the Mediterranean, ranges or spans this density range and salinity and temperature range over here. Mediterranean intermediate water, Mediterranean intermediate water is in this range with high salinity and relatively warm temperatures. North Atlantic deep water that we talked about forming here has this temperature and salinity range here, and the heaviest water, Antarctic bottom water, which is forming in the Southern Ocean, is way down here with this salinity and these cold temperatures. Okay, so this is the combination of water masses that are filling the subsurface ocean at various places. Okay. Just I will point out something else here. Because these curves are non-linear, the temperature and salinity relation to density is non-linear. What does it mean? If I take two water masses on this constant density line, one here which has a combination of, let's say, 10 degrees centigrade and some salinity, and another one over here which has, let's say, 15 degrees centigrade and this salinity, both have same densities, but I'm taking them from two different places with two different combinations of temperature and salinity. I mix them together. What happens? The temperature gets mixed up and you get an average temperature. The salinity gets mixed up and you get an average salinity. So the average temperature is going to be some 12.5 degrees, let's say, and average salinity is going to be something around 34 point something. So the density of that mixed water need not be the same as the two water masses which were at the same density. So you have now created the second density because the temperature and salinity combination will give you a different density even though they both started with the same density. This nonlinearity, it creates density driven circulation. It's called cabling, C-A-B-B-E-L-I-N-G, where because of the nonlinear density relation with temperature and salinity, you can mix two water masses of the same density and create a different density. Okay, this is kind of cute thing that happens in the ocean. Another way to look at this cross section is this. We are looking at the Atlantic again, going from the north to the south. So we have around Greenland, Gin Seas, Labrador Sea, we are forming deep, heavy North Atlantic deep water that's going to go south across the equator, and there is the Antarctic bottom water forming and sinking to the bottom and going to the north into the Indian, Pacific and Atlantic Oceans because it's heavier than the North Atlantic deep water. Antarctic intermediate water is lighter than the North Atlantic deep water, and the winds and divergence in this case is going to pull up the North Atlantic deep water. So we are looking at this cross section expanded here. So here is the Antarctic bottom water sinking to the bottom of the ocean, Antarctic intermediate water sinking below the surface. Here is the surface waters of the northern parts of the Southern Ocean, and you have intermediate water sinking above the North Atlantic deep water, and the North Atlantic deep water being pulled up by Ekman divergence Ekman is a word that is used generally in the ocean currents. They are wind-driven currents. When the winds create currents that diverge because of Coriolis or because of the wind stress curl, they are called Ekman Divergence, like in the East Pacific that we talked about, or they're called Ekman Convergence, like it happened in the subtropical gyre. So here you have Ekman Divergence, which means water is diverging, so colder water from below comes up, so North Atlantic deep water comes up here. So you have the Antarctic zone, Antarctic convergence happening here, so subduction or sinking of the intermediate waters and pulling up of the subantarctic zone, and so on and so forth. So this whole thing is something we saw before. Where the water is sinking, the age of the water is younger. We estimated this using the C14 isotope. If you remember, C14 is being formed in the atmosphere constantly. As soon as it goes underwater, it begins to decay, because in the atmosphere is decaying but constantly replenished by formation of the C14 with galactic rays, cosmic rays bombarding nitrogen, producing C14. But once it goes under the ocean, below the surface, there is no source, so it begins to decay, and you can track it and create ages, convert it to ages, which means when was the last time it saw the surface. So you expect youngest waters here. As you go north, you can see that older and older waters are seen. So North Pacific, which is the last endpoint of the thermohaline circulation, has the oldest waters. And there are also other evidences like oxygen and nutrients for that as well. And that water slowly gets converted to surface water and comes back. So you can see that this is over 2,000 years old. This is here only 400 years old. And here you have various ranges of 1,400 years and so on and so forth. Okay, so we will leave it here and look at penetration of anthropogenic heat into the ocean again. We have already looked at it a couple of times, but we will see how the ocean circulation creates special places where the heat can sink much deeper because of the thermohaline circulation. Okay.